300,000 downloads a month. That's the legitimate pull that PyTorch Lightning gets on PyPI. And that number is exactly why someone decided to impersonate it with a backdoored package designed to drain your browser credentials, your .env files, and your cloud service keys. Let's talk about what actually happened, what the malware does at a technical level, why ML teams are specifically at risk here, and what you need to do before you ship your next model training job. The malicious package was published to PyPI under a name close enough to the real PyTorch Lightning to catch people off guard. This is a typosquatting or namespace confusion attack, a technique that is not new but keeps working because humans are bad at reading package names carefully, especially when they're copying install commands from a README or a Stack Overflow answer at 11 at night. The legitimate package is maintained by Lightning AI and lives at PyTorch Lightning on PyPI. The attacker registered something adjacent. The exact variant name is worth checking against the bleeping computer write-up directly because these names sometimes get taken down fast and the specifics matter for your own audit. Once installed, the package executes its payload during the import phase. This is the part that should make you uncomfortable. You don't have to call any function. You don't have to do anything wrong beyond pip install. The moment Python imports the package, code runs. That code targets 3 categories of data. First, browser credential stores. On most developer machines, that means Chrome, Chromium, Brave, or Firefox profile directories where saved passwords and session cookies live. On Mac OS and Linux, those directories are accessible to any process running as your user. On Windows, Chrome's credential store uses DPAPI encryption, but the malware runs in your user context, so DPAPI will happily decrypt it for the process asking. The attacker gets your saved passwords, and more dangerously, your active session tokens for whatever sites you were logged into. Second, .env files. This is the one that should make ML engineers specifically pause. The pattern in ML projects is to keep API keys, database URLs, and service credentials in a .env file and load them with Python.env. It's a reasonable pattern for local development. It's also a pattern that concentrates all your secrets in one plaintext file on disk. The malware scans for these files and exfiltrates their contents. Third, cloud service credentials. That means AWS credentials files, typically sitting at ~/.oz/credentials, GCP application default credential files, Azure CLI tokens, and anything similar. If you've ever run Oz configure or gcloud auth application default login on the machine where you're doing ML work, those tokens are on disk, and the malware knows exactly where to find them. The exfiltration mechanism, based on what's been reported, sends this data out to an attacker-controlled endpoint. The specifics of the command and control infrastructure are unclear from the reporting at this point, but the collection and transmission pattern is well established in this class of attack. Now, let's talk about why this hits ML teams harder than a typical software engineering shop. A few reasons compound here. ML environments are notoriously messy with dependencies. A typical training environment might have 50 to 100 packages, many of them installed from notebooks, experiment scripts, or requirements files that haven't been audited in months. People install things to try them out. Conda environments accumulate packages. Docker images get built from requirements files that were assembled by copying from multiple sources. The attack surface is wide, and the hygiene is often worse than in production software environments. ML engineers also tend to have elevated cloud permissions. If you're spinning up GPU instances, accessing S3 buckets with training data, reading from and writing to model registries, or managing SageMaker or Vertex AI resources, your credentials have real blast radius. An attacker who gets your AWS credentials from a dev machine isn't just getting access to your personal account. They're potentially getting access to training data, model artifacts, inference infrastructure, and depending on your IAM setup, a path to production. The development machines themselves are often high trust. Researchers and ML engineers frequently work on machines that have direct network access to internal services, database credentials for feature stores, and API keys for third-party data providers. These machines are not always treated with the same security posture as a production server. They should be. There's also a cultural issue worth naming directly. The ML and data science community has a strong norm of sharing code, sharing notebooks, sharing environment files. That openness is genuinely valuable for reproducibility and collaboration. It also means people are accustomed to running code they found somewhere without auditing it carefully. That habit is being exploited here. So what do you actually do about this? First, check your lock files right now. If you use pip with the requirements, txt, look for any package in there that is PyTorch Lightning adjacent. The exact malicious package name matters here, so cross-reference the bleeping computer article for the specific string. If you use poetry, check your poetry. Lock. If you use pip tools, check your compiled requirements. The point of lock files is that they pin exact versions and exact package names, so if you have a lock file you generated from a clean install before this package existed, you're probably fine. If you don't have a lock file, you have a larger problem. Second, audit your PyPI dependencies for this class of attack more broadly. Tools like pip audit exist for a reason. Run it. It checks your installed packages against the OSV database and known vulnerability feeds. It won't catch every typosquatting attack because those often don't make it into CVE databases quickly, but it catches a meaningful slice of known issues. There's also a tool called Safety from PyUp that does similar work. Third, check whether you have any of these packages installed in existing environments. If you're using virtual environments properly, the blast radius is contained to that environment. If you've been installing things into a shared system Python or a long-lived conda base environment, assume compromise and rotate. Fourth, if you think you may have installed the malicious package, treat the machine as compromised. Rotate your AWS credentials, your GCP service account keys, your API keys, everything. Check your AWS CloudTrail logs for unusual API calls. Check your GCP audit logs. Look for any IAM changes, any new access keys created, any unusual data access patterns. The credential theft is the first stage. What the attacker does with those credentials depends on how fast you rotate them. Fifth, for your team going forward, consider requiring hash pin dependencies in your ML projects. Pip supports this with the require hashes flag. When you hash pin, you're verifying not just the package name and version, but the exact contents of the package you're installing. A typosquatted package with the same version number but different contents will fail the hash check. This is more operationally annoying, especially in fast-moving research environments, but it's the strongest defense against this class of attack. Sixth, think about your developer machine credential posture. AWS credentials stored in ~data/credentials with long-lived access keys are a liability. Consider using IAM Identity Center with short-lived credentials, or at minimum set up credential expiry and rotation. The same principle applies to GCP and Azure. Short-lived credentials mean a stolen credential file has a limited window of usefulness. One broader point worth making: PyPI's security model is fundamentally trust on first install. The package index does not verify that a package is what it claims to be beyond the name you registered. There are ongoing efforts around PEP 458 and SigStore integration to bring better supply chain verification to Python packages, and PyPI has been adding support for trusted publishers, which ties package publishing to specific GitHub Actions workflows. These are improvements, but they don't fully solve the typosquatting problem because a typosquatted package can also use a trusted publisher setup. The defense has to happen on the consumer side, through lock files, hash pinning, and dependency auditing. This attack is not sophisticated in its technique. Typosquatting PyPI has been a known attack vector since at least 2017. What's notable here is the target selection. PyTorch Lightning is a serious ML framework used by real engineering teams doing real work. Whoever built this package wasn't spraying and praying with a fake requests library. They picked a target with a specific user profile: engineers with cloud access, working in environments with lots of credentials on disk, in a community with relatively loose dependency hygiene. That's a calculated choice, and it suggests more attacks in this vein are coming. The real takeaway is this: generate a lock file for every ML project today, run pip audit against your existing environments, and rotate any cloud credentials that were accessible from a machine where you've been doing experimental package installs. That's not a long afternoon of work. It's an hour, maybe two. The alternative is explaining to your team why your training data bucket got exfiltrated.